Hello everyone, welcome to our daily physics problem, day 19. So today we are going to look at the problem that we looked at previous before. But now we are going to introduce a new way of solving this using a special trick that have a variety of usefulness. So you already solved it yesterday, so we're not going to solve it today. Today we're going to learn a little trick. So first, before we dive into solving problem, let's look at the statement. So there's a theorem called when three forces acting on an object in two dimension especially, the lines which the forces vectors are on intersect, have to be intersect at one point. So what does that mean? Let's look at the graph on the top. We know there are in this graph we have three forces, two tension force and a gravitational force. If we extend those lines further, and the gravitational force further, we see those three forces intersect on one point. That's a very, very important geometric features, because after we know the angles and the distance we're trying to solve, we can just use some geometry to solve for the distance between the center of mass of the system with the left hand side. So let's try to prove this theorem. Why is it true? First, let's draw an object, and then have three forces, random forces acting on it, on different part of the object. Let's define them as F1, F2, and F3. So now, because we know this force is balanced, object stationary, so we know that F1, the vector of F1 and F2 and F3, their sum is equal to 0. Okay. So now, then let's define another force. Let's say Fi is equal to F1 plus F2, the vector of F1 plus the vector of F2. Then let's look at behavior of F1, Fi. Fi is also the vector. Because we know that F3 plus F1, F2 have to equal 0. So F1 plus F3 have to be equal 0. The vector of F1 plus F3 have to equal 0. So we know the direction of F3 on the object is on the right. Then how are we going to cancel out this vector in order to be 0? Have to be exact the opposite direction and the same magnitude. Cannot be go upside, cannot be downside. That will provide extra torque, so it won't be stationary anymore. So in order it to be stationary, have to be on the same line, opposite direction, same magnitude. So F1 and F3 are on the same line. Proof is done. But now we haven't proved all the points yet. We need to prove they are intersect each other, not just one force on one line. Because there's a lot of way we can define Fi. We also define Fi as F2 plus F3. Then we can know that F1 and Fi are on the same line. If we define Fi equals F1 plus F2, blah blah blah, with some reasoning, we know that F2 and Fi are the same line. Then after we proved three forces, we know that those lines have to be intersect at one point. So that we know that F1, F2, and F3 are all on not all on the same line. They're all intersecting on the same point. Intersecting on the same point. Okay, so that's our proof. So now, after we know the proof, we can go back to our question. See how we use this proof in the solving process. So first, let's lay out all the angles we know, because two lines are parallel. We know this is theta, this is phi, this is 90 minus phi, this is 90 minus theta. Then by some rule of geometry, the trigonometry, we know that x divided by tangent theta is equal to L minus x divided by tangent phi. So we multiply both sides by tangent theta and tangent phi. We got x times tangent phi equal to tangent theta times L minus x. Then we move x to the left. we will have x times tangent phi plus tangent theta equal to L times tangent theta. Then we know x equal to L times tangent theta divided by tangent phi plus tangent theta. And that will be our final solution. I know it's a little bit different than we solved yesterday, because this one is derived from geometry and the yesterday one is derived from physics.